morning everyone. My name is Khaw and Ying. Today, my friend Siti Athirah and I would like to present about our Civil 3D assignment project. Before we show the results, let me briefly introduce the project. The study location is around Bayan, Lepas, Penang, Malaysia, and here is the satellite view from Google Maps showing the area. After setting up the project, I import the data and configure the coordinate system in Civil 3D. Here is the aerial views of the study area after completing the coordinate setup and importing the drawing. This ensures that our road's design aligns correctly with the real-world locations. As we can see, the study area contains many small hills and is also covered with dense forests. Building a road directly through these terrains could be difficult and unrealistic for our project. Therefore, we choose to focus on the boundary area just beside the existing road. These locations allow us to design and model the roads using Civil 3D, including the alignment, profile, and cut and fill analysis in a practical and manageable way. For our road designs, we adopt the U3 road standards based on JKR Arahan Teknik Jalan. The U3 standard is suitable for secondary or collector roads in urban areas with moderate traffic volume. It provides a lower geometric standard with partial or not access control, which matches the existing coordinations of our study area. Before presenting the result, we first explain the assembly used for the pavement design. The road was designed according to JKR Arahan Teknik for a U3 road type 2. For this standard, the lane width is 3.25 meters with a 2 meter shoulders on each side. The minimum road reserve width is 40 meters, which is appropriate for a secondary or collector roads in an urban environment. The design speed for this road is 50 km per hour, which is consistent with the U3 roads classifications. This assembly was then used to generate the corridor models in Civil 3D.
Hi everyone, my name is Athirah with my matrix number A180790, and for today, I will explain this section where I will explain the result of our proposed road profile and vertical alignment. This figure shows the longitudinal profile of the road along the selected alignment, where the red line represents the existing ground level and the blue line represents the proposed road level. The horizontal axis indicates the change, while the vertical axis shows the elevation. From the profile, we can see that the existing terrain is relatively undulating, while multiple small rises and depressions. Our proposed profile smoothed out these variations to produce a more uniform and controlled vertical alignment, while still generally flowing the natural ground to minimize excessive cut and fill. This approach improves driving comfort, construction feasibility, and long-term maintenance efficiency. The vertical alignment was designed in accordance with Arahan Teknik Jalan 8/86 Pindaan 2015, Section 4.3 Vertical Alignment. According to Section 4.3.1 and Table 4.10C, the maximum allowable gradient for a U3 road is up to 9%. In our design, the maximum gradient is approximately 3.77%, which is well below the allowable limit and therefore fully complies with JKR requirements, ensuring vehicles can operate safely without excessive climbing demand, braking issues, or discomfort to road users. The points labeled as VIP represent the vertical intersection point where two different gradients meet, and at each of this location, crest and sag vertical curve were introduced. These curves were designed based on Section 4.3.7 of Arahan Teknik Jalan ATJ 8/86 to avoid sudden changes in slope, improve driver comfort, and ensure adequate side distance, especially at crest curve, resulting in a smoother profile and safer road operation. Overall, the proposed vertical alignment achieved key objectives in terms of safety, comfort, constructability, and compliance. In conclusion, the proposed road profile is geometrically compliant, smoother than the existing terrain, and suitable for safe and efficient road operation in accordance with JKR Arahan Teknik Jalan 8/86. This curve. Next, I will explain the earthwork results, which are summarized in this total volume table. This table presents the cut and fill areas, individual volumes, and cumulative earthwork quantities along the alignment at each chainage. The cut and fill areas are obtained from road cross-section and are used to calculate the cut and fill volumes between stations, while the cumulative columns show the running totals and the net difference between cut and fill. From the final station, the total cumulative cut volume is approximately 705 cubic meters, while the total cumulative fill volume is about 3,838 cubic meters, resulting in a net earthwork volume of around negative 3,133 cubic meters, indicating that the project is fill dominant. This means imported fill material will be required, which is consistent with the vertical profile, where the proposed road level is generally above the existing ground. From a construction perspective, this has implications for material sourcing, haulage costs, and compaction control. In conclusion, the earthwork analysis provides essential input for construction planning, cost estimation, and earthwork management. Next, in highway construction, cut and fill analysis is the systematic engineering process of balancing earthwork operation by calculating exactly how much soil and rock must be excavated from higher elevation, which is the cut section, and used to build up lower areas, fill section, along the road alignment. This ensures a stable, properly graded road bed that meets the design specification for safety, drainage, and longevity while minimizing material import-export and transportation costs, turning raw topographic survey data into an optimized earth-moving plan that forms the foundation of the entire highway project. This selected table shows the cross-section level details at chainage 100 with a datum set at negative 10 meters. As it is shown in the figure, the red area represents the cut area, and the green area is the area that needs to be filled. The table compares the finished road level and the existing ground level at several offsets from the center line. From the values shown, the finished levels are generally higher than the existing level, indicating that this section of the road is predominantly in fill condition. In addition, our road design only needed a cut and fill process at certain areas, which are at chainage 100, 125, chainage 150, chainage 175, and chainage 200 because of the hilly terrain and still doable. The offset values represent the horizontal distance from the center line, where the zero offset corresponds to the road center and increasing offset indicate position across the carriageway and side slopes. This cross-section confirms the findings from the earthwork analysis, where embankment fill is required to achieve the proposed road geometry while maintaining a smooth and consistent crossfall for drainage and driving safety.
Finally, we come to the last part. This shows the object viewer of the horizontal alignment. The total length of the proposed road is approximately 341.68 meters. The alignment was designed based on a design speed of 50 km/h, following the U3 road standard. From the object viewer, we can clearly observe the overall alignment layout, including the straight sections and curved geometry, which were generated according to the design parameters set in Civil 3D. Next is the drive-through view of the design road. The drive-through demonstrates how the road fits with the existing terrains. The road geometry is continuous with smooth transitions between tangents and curves, providing a comfortable and safe driving experience. The drive-through speed is also set as 50 km/h, consistent with the design speed.